So I'm going to introduce Xiaotan Li as the colloquium speaker for this SOFA meeting, SOFA colloquium. So Dr. Xiaotan Li is a postdoc working at Dartmouth College with Yixin Liu. He obtained his PhD degree from the University of Alabama in Huntsville in 2016. And then he worked as a postdoc at the Los Alamos Lab with Van Gogh for a couple of years until, for 4 years actually, until early this year. So his current research focuses on addressing plasma energization and particle acceleration processes during solar flares using numerical simulations. So the colloquium is supposed to be 1 hour, but please leave some time for the audience to ask you questions. I'll give you some hints if it's time. Okay, so Xiaotan, please take it from there.
Okay, thanks for this opportunity to speak here. I will talk about large-scale particle acceleration during magnetic reincarnation in solar flares. And I want to thank my collaborators on this work for their help over the past few years. And my talk is going to have 4 parts. The first, I will briefly overview on particle acceleration during solar flares and a framework for studying particle acceleration. Then I will discuss particle acceleration and transport effects. In the third part, I will present a macroscopic energetic particle model and show some of its applications. I will conclude in the end. First, let's look at what motivates us to study particle acceleration in solar flares. Solar flares are among the most remarkable phenomena of energy release and non-thermal particle acceleration in our solar system. During solar flares, a large amount of magnetic energy can be released and converted into non-thermal particles within just a few minutes. The non-thermal particles can produce impulsive X-ray, hot X-ray, and gamma ray emissions that are commonly observed, and they can be released into the interplanetary space to produce impulsive solar energetic particle events. And the non-thermal emission play a critical role in our understanding of particle acceleration during solar flares. Since the Raci era, our understanding of particle acceleration in solar flares has been greatly advanced. The photon energy spectrum shown here indicated that electrons can be accelerated to MeV energy and ions up to GeV energy. And the observation indicated that a large fraction of the electrons in the flare region can be energized. And the hot X-ray photon spectrum often ensemble power distribution, which could be produced by power law or double power law electron distributions. And the X-ray image tell us that most of the non-thermal emission come from the focal points, and but this does not mean that the acceleration sites are at the focal points. Particles can be accelerated elsewhere and transported to the focal points, where the plasma density is higher and the emission will be stronger. Over the past few decades, our understanding of particle acceleration during solar flares has been guided by the standard flare model. Here's one example by Shibata et al. And in the standard flare model, the primary magnetic energy release is thought to occur above the flare loops, and probably by magnetic recreation in this elongated current sheet. And a lot of particle acceleration mechanisms have been proposed to explain the non-thermal emissions. For example, it has been proposed that particles can be accelerated by recreation itself, by recreation-driven turbulence in the recreation outflow, and by termination shocks driven by recreation outflow, and by, for example, large-scale orphan waves in contracting and bouncing flare loops. The particle accelerated in the coronal region can precipitate to the chromosphere and produce observed Hawk X-ray and gamma ray emissions at the full points. So all these mechanisms could be important for particle acceleration in solar flares, but since recollection play a driver here, it's essential to understand whether and how particles accelerate in the recollection region. More and more evidence have shown that a particle can be accelerated by recollection, and a key observational signature is about the loop Hawk X-ray emission, first reported by Masuda et al. In 1994, and this about the loop-top Hawk X-ray emissions indicate that the electrons probably accelerated by the electrons accelerate about the flare loops and probably close to the flare recollection site. But this does not rule out the possibility that electrons can be accelerated by recollection-driven turbulence or the termination shocks above the flare loops. And the recent radio observation actually provide more direct evidence of recollection accelerated electrons.
Xiaochan, could you use your cursor so we can see what you're pointing at, perhaps?
Oh, sure. Okay.
Thank you.
And here, for example, using the Jansky VLA, Bin-Chen et al. Showed that the electron beams originate from this very compact region that is likely to be the recollection site. And recently, YOFSA observation shows the microwave emission can fill up this whole recollection region, suggesting that electron acceleration could be very efficient in the recollection region. And for ions, the evidence for recollection acceleration is not as good, and but the observation do indicate that the same mechanism could accelerate both electron and ions. Here, the plot shows the very good correlation between the Hawk X-ray fluence produced by electrons with 0.3 MeV or higher energy and the gamma ray fluence produced by ions with 30 MeV or higher energy. So this good correlation suggests that the high energy electrons and high energy ions are probably accelerated by the same mechanism, which could be recollection. In the rest of the talk, if not specified, I will talk mostly on acceleration, electron acceleration. Modeling particle acceleration in solar flares is very challenging because first, the scale separation in solar flares is enormous. The typical size of solar flare is about 10 to 80 meters, and the ion inertial length is only a few meters, and in solar flares, and it is already the largest of the kinetic scales. Other scales like the valence or electron gel relays are even much smaller. The largest 2D peak simulation can have a size of a kilometer, and this is already based on reduced parameters, for example, mass ratio or net speed. The 3D simulations, 3D peak simulations are even smaller. And this larger scale separation makes it impossible to study particle acceleration just use a single gen simulation. And the 3D physics makes this even more challenging, as both peak and MHD simulations have shown that the recollection can self-generated plasma turbulence and the recollection layer become really complicated. And last but not least, the recollection have indicated a large number of particles can be accelerated during solar flares, suggesting that the accelerated particles could contain enough energy to change the plasma dynamics. Thus, the feedback from energetic particle to plasma could be important. So how are we going to model particle acceleration during solar flares? Two methods are often used in the community. First is we just focus on the small scale, use kinetic simulations. And this simulation can self-consistently evolve particles and fields, and is suitable for studying the acceleration mechanism and the turbulence properties. But as mentioned previously, their size are usually too small. And the other method is a test particle simulation, which usually coupled with MHD simulations. These simulations can capture large scale dynamics, but they usually don't include, for example, wave-particle interaction and feedback. And the energy spectrum obtained from this simulation are usually too hard to explain the observed spectrum. So is it possible to combine these two measures in a framework to study particle acceleration in solar flares? We have been working on building a framework like that for studying particle acceleration in flares. In this framework, there's 5 components. We use kinetic simulation to study the particle acceleration mechanisms and the turbulence properties and their roles in particle acceleration and transport. And we parameterize this as a acceleration and diffusion term in a macroscopic energetic particle model. And we can solve this model with high-resolution MHD simulation to provide accurate flat geometry and large-scale magnetic field and plasma flows. And the advantage of this model can provide spatially and temporally dependent energetic particle distributions, and which can be used for emission modeling. And the obtained emission maps from different wheeling perspectives can be compared with non-thermal emission observations. And then we expect this observation model comparison will help us improve the model and interpret the observations. Here, that's my brief overview of the particle acceleration during solar flares and this framework for studying particle acceleration. Next, I will discuss on the particle acceleration mechanisms and the role of turbulence in particle transport based on kinetic simulation results. Historically, it's thought that particles can only be accelerated at the recollection x points by the non-ideal electric field. But recent progress have shown that the Fermi mechanism could be very important in accelerating particles in magnetic recollection. For example, particles can reflect off the recollection outflow and gain energy through this Fermi reflection, Fermi mechanism. But the energy gain by this one reflection is usually insignificant, especially for electrons. So to gain significant energy, particles need multiple reflections of the recollection outflow. Recent studies have shown all kinds of possibilities to achieve that in recollection. For example, particles can circling around this contracting magnetic island and interact with the flow driven by this contracting magnetic island, and particles can also bounce between the 2 merging magnetic islands and gain energy. And some particles may be trapped in this recollection X line by an electric potential, and they can experience multiple reflections from the recollection outflow. And some particles can be pitch angle scattering by turbulence, and for example, when they leave the recollection exhaust, they can be scattered back to the outflow and experience more reflection from the outflow and gain more energy. So that's how Fermi mechanism works in a recollection layer, and we do need a multiple reflection of the recollection outflow to gain significant energy. Here's one electron trajectory from a 2D peak simulation showing the contracting island scenario. The top panel shows the electron trajectory, and we can say that the electrons are confined in 3 magnetic islands with different sizes. The electron continues gain energy when it bounces off this 2 ends of this magnetic island. And as the electron gain energy, we can see that it's continuous drifting along the y direction. Y direction is the out-of-plane direction shown in the top panel. And this drift suggests that a particle acceleration could be associated with particle drift motions. So how do we quantify that? So in the guiding center approximation, the particle energy gain is due to the particle guiding center drift motions along the electric field and the biotron acceleration. And if we sum all particles in one species, we will get the total plasma energization J dot E. The S here just for one species. So the J here, the current density, E is the electric field. And the perpendicular current density is due to the guiding center drift motions. Here, the two major terms are listed here. This first term is due to particle curvature drift, and which is corresponding to the Fermi mechanism Jim Drake always talk about. And the second term is due to the gravity drift. And there's also other smaller terms are not listed here. So with the perpendicular current density, we can study the contribution of different acceleration mechanisms. Here, the left plot shows the energization due to different mechanisms for electrons and ions. The red curve is for curvature drift, the blue curve is for gravity drift. So we can say that for both electron and ions, the energization associated with curvature drift is the dominant term. This is for simulation with zero Gauss field. A Gauss field is a magnetic field component that is perpendicular to the recognition plane. So when the Gauss field increases, the Fermi mechanism actually got a surprise. The red plot shows this result. The circles here are the energization due to the curvature drift. And we can see as the Gauss field is a horizontal axis. As the Gauss field increases, you can see it gradually decrease, suggesting that the Fermi mechanism becomes less efficient as the Gauss field increases. But keep in mind that this does not mean that the parallel electric field will be responsible for high-energy electron acceleration. As shown by Giordani et al., that the parallel electric field is actually very inefficient in accelerating high-energy particles. Starting from the drift acceleration, and Jim Drake's group have formulated a large-scale electron acceleration model called K-Global, and which has shown some nice results on electron acceleration. We take a different approach here because we found that the energization associated with drift motion is equivalent to these four terms, and the two of the middle terms are highlighted here. The P parallel and the P parallel are the parallel and the perpendicular pressure. The VE here is the equal speed drift velocity. P is the scalar pressure. So the second term is the commonly saying the compression term. And the third term is proportional to the pressure anisotropy and sigma ij. Sigma ij here is the shear tensor of the in the equal speed drift plasma flow. So for the shear acceleration, we can say the proportion to the pressure anisotropy indicating that it's only effective for anisotropic particle distributions. And this plot here shows the contribution of the different terms to the energization. It's very basic plot, but let's only focus on these two lines, the blue and the red and the blue lines without the dots. So the simulation shows that when the Gauss field is weak or moderate, these two terms will contribute over 50% of the total energization. When there's low Gauss field, most energization comes from the compression. The red line here, when there's moderate Gauss field, the compression and shear energization will become comparable. All right. So these results are based on 2D simulation, which are taught us a lot about the energy conversion and energy conversion processes and particle acceleration mechanisms. But 2D simulation has some limitations in studying high-energy particle acceleration. And in 2D simulations, high-energy particles tend to be trapped in magnetic island. And here's one example from a 2D simulation. The top panel shows the number density of high-energy electrons with energy of 80 to 160 times of inertial thermal energy. So we can see that the high-energy electrons are mostly trapped in these two islands. And the corresponding bottom plot shows the acceleration rate associated with the particle curvature drift. And we here the equal speed drift velocity cut by the magnetic curvature. The red region is indicated that the electron, red region indicated region where electrons can be efficiently accelerated. But we can say that high energy particle cannot access these regions because of this trapping. So their acceleration will become slower and slower as the simulation evolves, and when they are trapped deeply into the large magnetic islands. So we think that two aspects of 3D physics can help electron acceleration here. The first is that the magnetic field lines become chaotic in 3D simulation. The top plot shows the 20 magnetic field lines starting from very close points very close to each other. Within just one crossing of the system, the field lines can access a broader region of the reflection layer. So we expect that particles following the field lines will access multiple acceleration regions and gain more energy. And the second aspect of is that the 3D reflection will self-generate turbines. Here, the bottom plot shows the magnetic power spectrum in the K space at 6 time frames. So we expect that particles will experience pitch angle scattering in the self-generated turbines, which will prevent them from being trapped in magnetic islands or flash loops. And note that the spectrum in the self-generated turbines is very steep, which is different from the standard turbines models. And the similar results are shown in, for example, MHD simulations. But there's currently no agreement on whether this is the case, whether this is general at all. To show the 3D effects, we trapped high-energy particles in a simulation. Here's one example, one trajectory from the simulation. The top panel shows the projection of the electron trajectory onto this XZ plane. The trajectory is color-coded by the particle kinetic energy. The bottom panel shows the electron X position versus its kinetic energy. The number 1 to 5 indicates the different phases of acceleration. We can see that electrons first experience 3 phases of acceleration in the beginning, but then it got trapped in this large flux loop at the boundary. And the acceleration becomes slower and slower. If this is a 2D simulation, the particle will get stuck there forever. But this is a 3D simulation because of the chaotic magnetic field lines and plasma turbines. And this particle can escape from this trapping by the flux loops and experience like 2 additional reflections of the reflection outflow and gain more energy. This shows the importance of the 3D physics in particle acceleration. And to further illustrate the fast spatial transport, we also performed some test particle simulation using the Pixel field as background. Here, the terminal reflection layer is overplotted with a few magnetic field lines. Initially, the test particles are very close to each other, and just after a short time, the particles can occupy the whole reflection region. So this fast electron transport, the consequence of the fast electron is significant, shown in this red plot. This plot is similar as the one we have seen for the 2D simulation. The top plot is for high-energy electron distributions. The bottom plot is for the acceleration rate associated with the curvature drift. So because of this faster spatial transport, the electrons can access these red regions and get more energization. And that's indeed the case. Here I show the time evolution of the particle, the electron energy spectrum in the 3D simulation. So we can say the spectrum developed a power relative with power index -4 in the 3D simulation, and which persists throughout the nonlinear recursion phase and until saturate. And the embedded plot compares this with the 2D corresponding 2D simulation at 3 time frames. The solid lines are for the 3D simulation, the dotted line are for the 2D simulation. So you can see the electrons can be accelerated to higher energy in the 3D simulation, and the hand details keep growing as the simulation evolves. In contrast, in the 2D simulation, the maximum energy does not change after some time, and the flux keep panning up at the low energy, making the spectrum steeper and steeper. So this shows that the 3D physics can help particle acceleration in recursion. To quantify the effect of 3D physics, we calculate the energy-dependent particle acceleration rate. The acceleration rate is defined as particle energy change rate divided by particle energy. Here, the level plot shows the acceleration rate associated with different acceleration mechanisms. The horizontal axis is particle energy loudness by initial thermal energy. So we can say that the primary acceleration is due to a Fermi type mechanism associated with curvature drift, is same as in the 2D simulation. And the acceleration associated with paraelectric field and a gradient drift are irrelevant here, or even give deceleration for high energy electrons. And more importantly, the acceleration rate in a 3D simulation is a nearly constant. That's usually assumed for a Fermi type acceleration, but that's actually not the case in the 2D simulation, as shown in the red plot. Here, the red plot shows the energy-dependent acceleration rate at 2 time frames for 2D and 3D simulations. So we can say the acceleration rate in a 3D simulation for high energy particles is nearly a constant, but actually they fluctuate a lot in the 2D simulation and even become negative in the 2D simulation. So that's the 2 important factors for the formation of the power distribution in a 3D simulation, which is associated with the self-generated turbulence. So although the turbulence is very complicated, it actually help particle acceleration. And also, as I mentioned previously, particles are experiencing pitch angle scattering. So we expect that the anisotropy level in a 3D simulation will be lower. Here's one example in a 2D and a 3D simulation, the solid line for 3D, dashed line for 2D. So the anisotropy level 1 indicated the distribution is nearly isotropic. So we can say that the anisotropy level in general is lower in the 3D simulation than in the 2D simulation. Later in the 3D simulation, the anisotropy level is close to 1, indicating that the high energy particles are nearly isotropic in the 3D simulation. So remember from previous results that among the acceleration mechanisms, the acceleration associated flow shear is proportional to the pressure anisotropy. And this nearly isotropic particle distribution indicates that we may ignore the acceleration due to flow shear in modeling large-scale particle acceleration. So here's the summary on this part. We have been working on building a particle acceleration model to study particle acceleration during solar flares. And the model should be based on kinetic simulation results. So we have learned from kinetic simulation that the primary acceleration mechanism is due to flow, compression, and shear. And the shear is proportional. It is only effective for particles with anisotropic particle distributions. And we found that fast spatial transport of energy of particles is very important for particle acceleration and the formation of power law energy distribution. Whether the transport is a diffusion process still needs a lot of study. And we found that turbulence could lead to more isotropic particle distributions. But again, we need more studies on this with simulation with different plasma parameters. And we found that turbulence spectrum is different from the standard models. So there's a lot of unknowns about the particle acceleration and transport in reconnection. So shall we get everything ready first, or shall we start building a model and with some assumptions? And we decided to build a model first and then gradually improve it as we learn more from the kinetic simulations. As the next part of the talk, I will show some initial results from this model. So we start from the classic particle transport equation, where the first order acceleration term is due to flow compression. And the assumption here is that the particle distribution is nearly isotropic. If that's the case, the flow shear is a second order acceleration term. And we further assume that the particle transport in a self-generated turbulence in reconnection is a diffusion process. And we assume that the turbulence spectrum is a common Gorodov lag. But the model is built to be flexible to change between the different turbulence spectrum. So the kappa IG here is the spatial diffusion coefficient. UI is the plasma flow velocity. VDI is the particle drift velocity. DPP here is the momentum diffusion coefficients. Q here is the source term. We solve this equation using the stochastic integration method. And magnetic field and plasma flows are provided by MHD simulations. Here's one example of the MHD simulations. To show the 3 frames of the current density in the MHD simulation, we can say that as the simulation evolves, the current sheet becomes unstable to the tearing mode instability and breaks into a series of magnetic islands. These islands tend to merge and contract. And the merging process will lead to very large magnetic islands. New magnetic islands are continuously generated in this reconnection current sheet. During these processes, the plasma density in the reconnection layer increases from the background value 1 to 3 or even higher, especially in these island regions. So we expect that particles crossing this region will experience acceleration and by flow compression. It's indeed the case when we solve the linear particle model with MHD simulations. We found the significant particle acceleration here. The particle distribution in simulations with different Gauss field. For these two plots, we use constant diffusion coefficients, and we can see that the spectrum develop polar tails, and as the Gauss field increases, the polar tail becomes steeper, and the maximum energy becomes smaller. For the Gauss field 1 case, the spectrum is really steep. This suggests that additional mechanism might be necessary for particle acceleration in high gap field case. And as will be shown in the next slide, a different diffusion model can also help. And the dependence on gap field is consistent with the solar flare observations. So according to quasi-linear theory, the diffusion coefficient should increase with particle momentum here. The increase with p to the 4/3, according to the theory. And the theory also shows that the perpendicular diffusion should be much slower than the parallel diffusion. Here we use the ratio between the perpendicular diffusion and parallel diffusion about 1%. And we found that now the spectrum has spectrum breaks, and the maximum range become lower. Interestingly, that with this diffusion model, the particle energy spectrum when the gap field is higher, actually the spectrum becomes harder. That actually helps the particle acceleration. And the power law indexes are mostly consistent with observation, which usually shows a very broad distribution of the power law indices. As mentioned, that one advantage of this model is that it can provide spatially and temporally dependent particle distributions. Here's one example of the high-energy electron distribution in one of the simulations at the 3 time frames. So we can see early in the simulation, most of the high-energy particles are concentrated in some local regions where the acceleration could be more efficient, for example, in this end of this contracting island or in this island emerging regions. But as the simulation evolves, the particles will be convected with a reflection outflow and distributed to a broader region. But even at the end of the simulation, when the distribution is more uniform, there's still some hot spots, for example, at the 2 ends of the large island. So this distribution can be input for non-thermal emission modeling, for example, by GS signature. The produced emission maps can be directly compared with observations. We have been using this model with MHD simulation with more realistic initial and initial condition and boundary condition. Here's one example with non-tied with MHD simulations having non-tied boundary at the bottom. The top plot shows the spatial distribution of high-energy electrons at the 2 energy band. You can say that most of the high-energy electrons are concentrated in this about the loop top region, and some of them is in this island region. And the bottom plot shows the spectrum at these 4 boxes. As expected, we can see that most of the high-energy particles are in these bottom 2 boxes. And here we use a constant diffusion coefficient. That's why the spectrum has a very extended power law tail. And here's another example is 2D Forbes-Lee model, where the non-elongated current sheet can self-consistent form above the flare loops and during the eruption of this large flux loop. And we see a series of magnetic island is generated in this current sheet. And when we solving this energetic particle model with MHD results, we can get the map of the energetic electron distribution. Here's one example. We can say that the high-energy electrons are mostly concentrated in island and in the loop top region, which are largely consistent with observations. So here's a summary on this part of work. So we have been working on building this macroscopic kinetic model. And in the diffusion limit, solving this model using Parker's transport equation leads to the formation of power law energy distributions. And the advantage of this model is that it can produce spatially and temporally dependent particle distributions that can be used for emission modeling. And based on the initial results, we are currently working on improve this model. For example, first we are trying to include the additional acceleration terms, for example, moment diffusion terms due to flow shear and wave particle interactions. And we are including spatially dependent particle injection and turbulence properties. So we expect more particle injection close to regions where the current density is stronger. And as indicated by observations, the turbulence should be stronger in the current sheet and in the loop top regions. And we are currently working on extending this model to 3D. Here comes to my conclusions. Again, we are working on building this model. This model has different components. We use kinetic simulation to study acceleration mechanism and turbulence properties. And we parameterize this as a acceleration diffusion term in a macroscopic energetic particle model, and then solve the model with MCD simulation that can provide accurate flare geometry and magnetic field and plasma flows. The model can give spatial and temporal dependent energetic particle distributions that can be used for emission modeling. The emission maps can then be compared with observations. So we expect the observation model comparison will help us improve the model and also help interpret the observations. And here are a few takeaways. First, the particle acceleration in reconnection mostly due to flow compression and shear. Second is that the self-generated turbulence in 3D reconnection is very important for particle acceleration and transport. Third, a macroscopic model including just simple acceleration terms, for example, compression acceleration and spatial diffusion, can lead to efficient particle acceleration. And the advantage of such model is that it can produce observable signatures. That's all I have. Thank you for your attention. I would like to hear your comments and take some questions.
Thank you very much, Xiaotan, for this wonderful talk. So, if you have any questions, please feel free to unmute your microphone and let Xiaotan know.
Hi, Xiaotan. I have a few comments. I think this is a very nice progress. I think your work is very complementary with Jim's group. For your peak study with, very complementary with Joe's study. And your large scale model is, I think, very complementary with this global model that Jim and Harry have been developing. But I think maybe we are actually very much agree upon the acceleration mechanism. But it seems to be differences in terms of how particle transport, especially the mechanism for that. K-Global starts with a scattering-free assumption, and you are doing the basically complete isotropic assumption. I think both of the models maybe need to include some macroscopic scattering mechanism. I'm particularly very interested in this visceral wave scattering mechanism that Jim has presented. I think maybe both of the models need to include that. And another thing, I think observations showed strong evidence of scattering, as we discussed yesterday, you might have missed that. But it seems like there is the conclusion we made yesterday is that we cannot singly based on observation or simulations because neither of them can give us the definite answer on how much scattering there will be. So more, comparison between modeling and observations and what, your model and K global model can predict different answer will be very helpful. That's just my comments.
Mm-hmm. Yeah, that's a very good comment. And yeah, I do think that we can learn from different perspectives, for example, using different models to study the same events or same observable signatures.
Xiaokant, this is Jim Drake. Can I also ask a question that's related to what Fan just talked about, which is the scattering? So in your talk, you showed that that the high energy particles in your simulation became essentially isotropic. Mm-hmm. And so I was a little surprised at that because we're not really seeing that in our simulations. And I'm wondering whether that they become isotropic because their energy is sufficient so that they're no longer magnetized in the turbulent state that you're producing. And if that's the case, then do you think that's going to continue if you go to a much larger scale system in which it's likely that the turbulence scale lengths become much, much larger than we can actually do in a PIC simulation?
Mm-hmm. Yes. For the actual anisotropy, and I mentioned that this is only for one simulations, and this is fairly low gap field. I think the gap field is 0.2. Actually, when you increase the gap field, the anisotropy will become pretty large. I think when you increase the gap field, the turbulence level will become lower. And the other thing is that I think your comment is that if there's a very large scale, the turbulence level at the kinetic scale will be very low. And I think that it's based on, for example, the cascade of the turbulence from the large scale. But for reconnection, we don't know actually that's the case for the formation, the turbulence. There's a simulation suggests that the formation in the turbulence actually in reconnection could start from the small scale and then cascade to large scale. So in that case, I think that the turbulence level at a kinetic scale is not necessary to be very small for the time scale of the particle acceleration. But I don't think there's a conclusion of that. That's just my understanding at this stage.
Oh, thank you.
This is Hugh Hudson. Can I ask a question?
Mm-hmm. Go ahead.
The question is, what density, what turbulence magnitude do you envision? I mean, is in terms of just ordinary pressure contribution, delta V over B, that sort of estimation. What level of turbulence do you really need for a realistic particle acceleration model?
For our current test, we assume that the turbulence level at the outer scale is delta B over B is about 1. But we don't know what is outer scale in a reconnection-driven turbulence at this stage.
Yeah, but to get sufficient particle acceleration, what turbulence level do you need?
currently we just assume that's 1, probably around order 1. Yes.
So what does that correspond to in erg? That's
erg, okay. I don't know.
Difficult question, sorry.
That's a very good question. I don't have a number for that, but usually we use that, we assume that the turbulence, the fluctuation is at the large scale, means the order scale is the same order as the background field. So I don't know if that's how to estimate it using flare parameters in that case.
Can I ask a question? This is Ty. So early on, you talked about, when there's a guide field, the Fermi acceleration becomes less important and curvature drift becomes more important, right? And then later on, when you talked about why you get power law, and there you said the Fermi was dominant. Can you clarify that? Did you then talk about the small guide field case when you talk about power law, or?
So the curvature drift corresponding to the Fermi mechanism. So when the guide field increase, the acceleration due to the curvature drift will get less efficient, and it's the same as saying that the Fermi mechanism become less efficient. But the problem is this is based on very small scale simulation, and we don't know. For example, we can simulate like a very large box is the conclusion still holds. Because in a small scale simulation, the acceleration close to the reflection X line by the parallel electric field become very significant. But this simulation is much smaller than the really flare reflection side. So we currently don't have a conclusion whether it will be still like this in a much larger simulation box. And I think Joe Danin's results indicate that the parallel electric field is inefficient no matter what in accelerating high energy electrons, because for Fermi mechanism, the energy dependent, the acceleration is proportional to particle energy, but that's not the case for the parallel electric field.
Right. So, but when you have a guide field, how do you get power law?
When the guide field, I didn't really touch a lot about the formation of power law here, but actually, even there's a guide field, you can show that for the high energy particles, the acceleration is still mostly due to the Fermi mechanism, because the previous results I showed mostly based on the average over all particles. But if you can calculate the energy dependent particle acceleration, we can say that the acceleration and high energy will still mostly due to the Fermi mechanism.
Okay, thank you.
So Xiaochan, I think you are basically saying the acceleration rate will be lower. That will lead to a softer spectrum. And that seems to be consistent with what Harry is getting for the K-global simulations.
So fine, what you mean is for large guide field, the acceleration rate is less and it'll be softer.
Yeah.
Just to clarify.
Yes. There is a figure on that in Xiaochan's talk, I think.
This is Joel DeLee.
Oh, that's one.
Yeah, there's a comment that looks like even at guide field 1, you still have, this is what we found in our simulation, and it seems clear from your simulations also. That's not that the Fermi mechanism is completely gone. It's just, for the overall bulk energy gain, E-parallel and Fermi are both operating. But as you mentioned, Fermi preferentially drives the higher energy particles.
Yeah. That's right. That's right. So any other questions, comments?
Yeah, we still have time for a couple quick questions.
Another quick question, this is from you again, is the coupling of scales. If you want to do the test particle approximation for the particle transport, it's difficult at higher energies because the particle ranges can be so large. And so in general, in principle, the accelerated particles have to form a different gas, which may contribute strongly to the pressure of the medium. And so at some point you lose the ability to do a prescribed geometry. Can you comment on where that may happen or where that may be important?
That's a very good question. That sounds like a lot in the key global model can deal with. I think in that model, it includes
what I'm saying is the global model can't deal with that because you have this acceleration process that's microscopic, and yet the particles escape from the acceleration region and influence their larger scales.
Oh yes, I'm not. I didn't mean the global model. I mean the Jim Drake's groups model. So in their model, they include the feedback of the particles, either through the energy terms and also current, back to the plasma. And I think they show that they could change the plasma dynamics through the Feldhaus instability. Is that right, Jim?
Yeah. So the K global model, for those of you who haven't been following this, what's the development of that? It includes both the kinetic acceleration processes, but at the MHD type scale. So in principle, we will be able to do a macro system like you were referring to, while at the same time looking at the feedback of those very energetic particles on the MHD field. As you might have guessed from some of the questions that came up during this talk, and we had an extensive discussion of this also yesterday in the group 3 of the sulfur project, the transport issue is, and the scattering issue in particular of the energetic particles is crucial and remains something that we really don't understand very well, but we're going to have to figure this all out if we're really going to be able to look at how the most energetic particles get transported both within the energy release domain and as they propagate down towards the chromosphere.
Can I ask one question? Do you have time? So, when you show going from 2D to 3D, the flux of energy of energetic particle electrons go up, but does the slope really become harder, or just the number of particles, energetic particles, go up?
Actually, the slope become a little bit harder compared with 2D simulation, because in 2D simulation, so you can see the flux just keep increase around these energies. Mm-hmm. So as the simulation evolves, it's going to be getting steeper and steeper. But in the 3D simulation, the slope is really steady.
Mm-hmm. Okay.
Yes.
Thank you.
Okay, so if there's no other questions, it's already 2 o'clock, right on time. Let's thank Xiaotan again with some fake applause. Okay.
Thanks.
Thank you all for joining the program.